All right, so let's go over the exam. It's exam 2. And this material is really important. If any of you, and many of you, are going to be involved with computer programming, regardless of your major, and understanding user-defined data types or classes is just essential. You just have to know this. So it takes a while to break the ice of understanding and get through it. But once you get it, then it's not a problem. It's really easy, actually. It's very easy, and it helps when you're coding, when you're writing a program, reading other people's code. It just opens up a whole new world of possibilities and opportunities for you. So it's an essential understanding. And what we're doing in this first class is just giving you the very beginning of object-oriented design. So we're just learning how to define a class and then how to call it using test cases. That's all that I'm covering. And when you go on to do other work and take other classes or even do other work outside of class, that you'll learn more about these classes and objects. And there's things called inheritance, polymorphism, and lots of other things that, not lots of other things, but a few other things that you need to grasp, especially inheritance. So let's go through this exam pretty completely, and then and I'll try to explain the essence of what a class is and how to work with it. That's what I want you to grasp this. And I think a lot of students are trying to memorize stuff for the exam, and and you have to memorize some things, but essentially what you need to do is grasp the essence of it. You have to understand what it is and how to work with it. So it's probably better for you to spend more time practicing programming. So create a class, create test cases for it, and play with it. Read about it, and come back and do some more experiments. If you're coming in late, you can get your exam down here on the table. You're welcome to look through the pile. So let me show you how I think you should approach this, say in a practice session. You'll be taking a final exam at the end of the quarter, and we'll have another big problem on it. It'll look just like one of these problems that are in the exercises or on this exam. So I'm going to go through a session and make it look like what I think you should be doing when you practice. Okay, this is how I think you should practice. First, I'm going to create the test harness or the test code.
Missing that.
So I'm just going to get the basic code to run here. All right, let's see if that runs. There it goes. Looks good. Now, we're going to follow the standard pattern, which is to store the class declaration in a file by the name of the class. So it's, was it number in the exam?
Fraction.
Oh, fraction. Fraction dot h. And that's it. And then we'll create an instance of a fraction. We'll call it, say f1. And we're going to pass in the numerator, which is the number on the top, and the denominator, which is the number on the bottom. And now we have f1 as a fraction. So we're creating an instance of our data type called fraction. And the information that we pass in is the numerator and the denominator. So that's going to be stored internally in the object that gets created. F1 is a reference to this computer object, this object that's resident in memory, and it stores that information, 8 and 6, inside of it. So the constructor, you're going to implement the constructor. You're going to take that 8 and that 6. You're going to store it in the member variables for the numerator and denominator. And then we do things. We're going to call functions on F1 to test it. So F1, there was, what is it? Is improper, right? So is improper is true. So this is an improper fraction because the numerator exceeds the denominator. So that's the definition of an improper fraction. And what other functions do we have with that we need to test? No, on the exam, I just asked you to test one. I don't remember which one it was. But what are I want to test all of the functions. What's another function on there? Is it like get numerator? Get numerator, right? So get numerator, that should be 8. And get denominator. Denominator, and that's 6. What's another function? Oh, is lucky, right? Which, you know, I was meaning to, is it is lucky or is unlucky?
Is lucky.
Is lucky. And I didn't ask a, did I get that right? Is lucky? Yeah, okay. I didn't actually meant to ask you to implement this function, and I forgot, you know. So that was, I intended to have that on the exam, but I didn't get there. But in the problems coming up that I'm going to be, I use this is lucky, is unlucky concept to for some problems coming up. So let's look at that. What other functions do we? Oh, we have simplify, right? So that's the hard one, by the way. There was one hard problem on the exam. It was simplify. And you know, some people got it, which is fantastic. You know, that was a hard problem. So we're going to call simplify. Now, simplify doesn't return any value. So we don't put it inside of an assert. We just call it. Now we have to check its effects. After we simplify it, the numerator should be 4, and the denominator should be 3. That's the simplified form, right? So we want to reduce the numerator and the denominator by common factors. The common factor between 8 and 6 is 2. So we take a 2 out of both of those. Are there any other functions? Am I missing a function? Oh, lower bound, right? Was it lower bound?
Integer lower bound.
Integer lower bound. Integer lower bound. So that's the largest integer that's less than or equal to the fraction. What is the largest integer less than or equal to 8 over 6?
1.
That's a 1, right? 2 is too big. That would be 12 over 6 would be 2, right? 6 over 6 is 1. So 8 over 6 is bigger than 1, less than 2. So the biggest integer less than or equal to 8 over 6 is 1. That's called a lower bound. All right, so now we can also you know, that's where we just create one fraction. We can create another fraction, say F2. And we'll make this, say 4 over 8. And the And when we simplify it, the numerator should become 1. And the denominator should become, the denominator should become, what, 2. And is improper should become false. Or it is false. Is lucky, so it's a lucky number. Is this lucky? Is F1 lucky? What's the definition of lucky? What does it say there?
In return, true, the numerator is divisible by 7, and the denominator is not divisible by 13. It returns true if the numerator is divisible by 7, and the denominator is not divisible by 13.
Okay, so the numerator is divisible by 7, and the denominator is not divisible by 13. That's the requirement to be lucky. All right. So these are still unlucky. So this is not lucky. So that fails. And let's create another one that is lucky. So fraction, say 14. If the numerator is divisible by 7 and the denominator is not divisible by 13. So say 27. So this F3 is lucky. The numerator is divisible by 7, and the denominator is not divisible by 13. Let's make another test case here to fully test our logic on the is lucky function. Let's see, 13 times 3 is 39. There we go. Now the numerator is divisible by 7, but the denominator is also divisible by 13, so it is not lucky. So the divisibility by 13 cancels out the luck of being divisible by 7. We'll say that one is false. So we could keep going with test cases, but those are the test cases that come to my mind that I think are important. Now this code won't run because we didn't define this class yet. So let's go ahead and do that. Remember, we use that pragma once because we don't want recursive includes to happen. And so now we define the class. Class number.
You mean fraction?
Oh, sorry. Thank you. Fraction. We need the constructor, and that's numerator. Denominator. And we have get numerator. That's a const function.
Denominator is misspelled.
What's that?
Denominator.
Get denominator? I didn't spell it right? What's that?
You're missing A. Missing in denominator.
Numerator. Did I get that right? Huh?
Denominator. One on the right.
Okay. Oh, I see. Denominator. I got it. Thank you.
That way you don't have to-
Got it. Thank you. Also, we have the set numerator and set denominator, and we don't have test code for that. But let's get it in there anyway. So this is these are not const because they modify the object that that they run against. So they are not constant. They modify the state of the fraction. And we should have test code for that. Let's put it here. So this F4 set set denominator to 40. Now it's lucky. And let's then set the numerator to numerator. Let's set that to 10. Now it's no longer lucky because the numerator is not divisible by 7. Everybody agree with that test code? All right, is lucky. Is lucky returns a bool. It's const because calling it doesn't modify the fraction. And simplify. Simplify is not const because it modifies, sorry, it's a void. It may modify the fraction. If it does a simplification, it will modify the numerator and the denominator. So those are the two pieces of data that comprise the internal state of the objects. All right, there we go. Did I miss anything?
Is improper.
Oh yeah, is improper. So that's bool. Is improper. That's const. And then finally, we need the private member variables.
We also need the integer lower bound.
What's that?
Integer lower bound.
Oh, integer lower bound. There we go. Actually, we need to, that's const, it doesn't modify the fraction. We need to have test cases for that. Oh, we do right here. This is the integer lower bound of 1. This should have an integer lower bound of what? What's the integer lower bound of 4/8? That's 0, right? All right, so that's that. Finally, we need the data, the numerator and the denominator. That's where we store the information we operate on. Now, we can compile this. I'm going to use -c. Oh, assert needs to be defined. Let's just compile main. See the -c, that means just compile, don't try to link. And it worked. You see that main.o? That's like an intermediate file that gets generated during the compilation process. That's called a object code. So it's mostly machine code, but it's annotated, and it's got, spots in it that the linker is going to modify, to resolve how to branch to functions that are in other compilation units. Namely, fraction.o, we'll need to generate fraction.o, and then those two object files need to be linked together as well as linking into the operating system. So we're not going to need that. I'm going to make a copy of fraction.h to fraction.cpp. And let's implement these functions. We need to include fraction.h, the header file. That declares the class. That tells the compiler what the class looks like. And let's go ahead and implement these. I'm going to show you an alternative implementation for the constructor. Maybe you haven't seen this yet, but if you go to read code or work with code, you'll end up seeing this. So this is called an initialization list, and it's followed by this colon. And then it's followed by the data, and with instructions on how they are initialized. So the numerator and the denominator, and then the function itself, which is going to be empty in this case. And maybe I'll put this on the next line, so we don't have to keep it on that line. So the numerator is initialized to the function argument numerator. So do it like that. When the compiler sees this, it doesn't get confused. In the initialization list, it knows that this is going to be a member variable. So we don't have to go to this numerator. Just say numerator. And the compiler knows that that's the member variable numerator. And then inside these parentheses, this is the locally scoped value that this numerator is going to be initialized with, which is that function argument numerator. And this is an alternative form for the constructor. Just so that you see that. Get numerator. All we do is we return the numerator. So because numerator is private, we don't let outside code access it directly. This is just a pattern that a lot of people follow. Some languages enforce it more than this language. And so we require the outside code to access the data, to operate on the data by calling functions. And these are called accessors. The get functions are called accessors, and the set functions are called mutators because they mutate, they modify the state of the object when they're called. So that's one accessor. Let's look at the other accessor is similar. And here are the mutators. So setting the numerator. Well, here we need to distinguish between the locally scoped numerator, the function argument numerator, and the member variable numerator. So use this numerator equals numerator. So there we have a scoping issue. We don't up here because the compiler knows that this first name is going to be a member variable and not a locally scoped, function scoped value. Here we don't have to use this denominator because there's no conflict in names. There's no other locally scoped denominator that is overshadowing the member variable denominator. But here in set denominator, this function argument takes priority. When we use that name, the compiler says, oh, that's the more restricted name. That's limited just to the function. And so we need to tell the compiler using this notation when we're using a variable that has a broader scope. There it is, denominator. Denominator. All right, what about is lucky? And simplify. And the rest of these is improper. Integer lower bounds. Is lucky. So it's lucky if the numerator is divisible by 7 That means the numerator is divisible by 7. That's true when the numerator is divisible by 7 and the denominator is not divisible by 13. You see that? That's the expression. The numerator is divisible by 7. That means you divide numerator by 7 and you get you get 0 as what do you call it? Quotient, remainder. And the denominator is not divisible by 13, means you divide by 13 and you never get 0 as a remainder. And this whole expression evaluates to true or false. So we just return that. And see, it's a condition with and. You have to have two conditions. To be lucky, you have to have two things have to hold, both of them. If either of these turn out to be false, then it's not lucky anymore. So if it's false that the numerator is divisible by 7, it's not lucky. If it's false that the denominator is not divisible by 13, or let's simplify that. If it's true that the denominator is divisible by 13, then it's not lucky. We could have done this, but maybe that's hard to get. And we could do it like this. If we don't want to use that, if we want to do something like this, that means the denominator is divisible by 13, but we don't want that. So I'm going to put a not in there, see? We can do it like that. Maybe that's easier to read. But I'm going to go with that because I like that. I think it's simpler for me. And what about is improper? We'll come back to simplify in a minute because that's the hard one. Is improper. So if the numerator, to be improper, the numerator needs to be larger than the denominator. So this expression, numerator greater than denominator, that evaluates to true when the fraction is improper. So we just simply return that, the result of that expression. You could say if numerator, just here's the alternative way to say that. If numerator is bigger than denominator, then return true. Else, return false. We could do it like that. But you'll see the programmers will write it like this because it's more compact. And eventually this will be easier for you to think about, to work with. It's less to look at. But in the beginning, it might be simpler to write it out like this. What about integer lower bound? So the hint there was to use integer division. That's it right there. So integer division gives you an integer lower bound. It truncates. If you have whatever fractional component is generated through the division, it's just discarded. That gives us the integer lower bound. Now simplify. Let's do this. So we need to have a loop because we don't know how many times the number 2 goes into a fraction, into the numerator and denominator of a fraction. So, if it's 64 over 32, then we're going to have to remove a lot of 2's from the top and the bottom of that fraction. And so what we need is a loop. And I'm just going to start with some kind of a while loop here. I don't know what condition I'll use yet. Maybe the common divisor, we'll call it n. We'll start with 2. And the thing we're looking for is if the denominator, sorry, I'll start with the numerator. If the numerator is divisible by n, and the denominator is also divisible by n. In this case, we can take the n out. It's just like that is lucky function. So you've got an and condition there. Two conditions have to be met. The numerator must be divisible by n. And the denominator must also be divisible by n. And when you have that condition, or those two conditions, then we can take out an n. I can write it like that. Let me not. I'm going to write it this other way. Let's write it like this. We can take the n out of the numerator, but we also have to do it for the denominator as well. And we could do it, say, while the numerator is, well, n is less than the numerator. We'll say something like that. This will do it. We need to have a stopping point. Now we need to increase n, but remember, if it's 4 over 8, we're going to need to take out two 2's from the top and the bottom. So we want to run this one twice. So once we take out 1, 2, we don't want to increase n. We want to try n again. The only time we increase n is if we reach a point where n is not a common factor. So we increment n when it becomes known that the n we're working on is not a common factor. Then let's look at the next one. So that, I consider that a hard problem, for a test. I mean, at this level. I mean, later on it's a really easy problem, of course. Does anybody see any problems with that? Yeah.
For 3,
Huh?
you still need to divide by 3 if it's like.
Yeah, and that's why we increment n, see?
Oh, okay.
So we're going to hit 3, then we're going to hit 4, then we're going to go all the way up until we reach the numerator. Now maybe the denominator is smaller than the numerator. Well, so what? It doesn't matter because n's not going to go into the denominator anyway. So this is good enough. We just need a simple way to cut off the loop. So when n reaches the numerator, then that's good enough. We could also use the denominator there, or the minimum between the two, or numerator divided by 2. I mean, all kinds of things we could use. Well, not divided by 2, but this is good enough. Now, I did this in a way that's inconsistent with my recommendations all along in the class, right? I said to do things incrementally, but we did everything all at once. We didn't even test it yet. Well, we tested the initial compilation. You have a question?
Yeah. So for the loop, like, what if the numerator is 2? Then the loop will never run. Then
if the numerator is 2, you're right. It will not run. Thank you. You've got the bug. You found the bug. That's very good. Thank you very much. But the numerator is 2. So if it was like 2 over 8, it's not going to run. Is that going to fix it? because we want to try 2. We want to divide out by 2, so we get a 1. Like it was 2 over 4, right? And then we take 2 out of the 2, that becomes a 1, and 2 out of the 4, that becomes a 2. And that's what we want. So thank you, that's good. Very good. Caught the bug.
And also for the functions, you forgot the scope operator. Fraction.
Which function?
For all the functions in this.
Oh, the scope operator. Thank you. That's a good name, scope operator. Thank you. So that's not going to compile. We need to tell the compiler that all of these functions are within the fraction class. So this is called a scope operator. Or the scope designator. Or maybe the scope label. Or the scope annotation. There are lots of ways to express that. There we go. Good. We're going to get a clean compile, maybe? How many people think this is going to compile and run all the test code exactly? Would you bet $10 on that? I don't know if I would. That bet would make me nervous. All right. Yeah, it's called fraction. Oh my gosh, I should have made the bet. Well, we don't know if the test code runs. Oh, that's incredible. Could have made $10. All right. That's because you got those 2 bugs. Otherwise, it wouldn't have worked. On my own, I wouldn't have gotten that. All right. You never won that bet on my own. All right. So that's it for the class. Any questions about this? You got to work with this, and I got to tell you how important this is. This is just, you got to know this. We don't actually use classes in this course. We're just this is just a baby step into this technique. Just learning how to define the class and maybe write a few test cases. And later, when you build larger systems, then you'll be defining classes that are actually useful to make a program run and keep the logic organized. Any questions on this? We have a few minutes left, and I want to say that we don't have a lot of new material to cover. Well, no, we have sorting actually, binary search and sorting. Those are kind of big. So do we have 3 weeks left? 2 weeks? Who knows?
More or less.
2.5 weeks? 3 weeks. Okay. So we're not going to learn any new concepts about the language. We're just going to work with the tools that we've learned so far. And the focus now is going to be on writing algorithms to do what's called linear processing. So we're going to give an array of integers and perform some operation on that array. So we'll be implementing these functions that do operations on arrays and vectors. And there's 2 operations that are particularly important or useful to focus on early on. And one is called binary search. The other one is sorting. So sorting means, you've got a sequence of values, but they're out of order. How do you put them in order? So write the algorithm, write the code that rearranges the integers that are in the vector so that now they're in increasing order. And then binary search is like, well, I've got a telephone book. Everything's in order already. What's the fastest way to get to something? Well, you split it in half. You open the telephone book in the middle, or the dictionary in the middle, and then you decide if it's to the left or to the right, and you zero in on it by cutting the amount of concern that the amount of data that could possibly contain the value, cut it in half each time. So that's a lot faster than going linearly through the data. The linear search is very slow. You have to look at the first page of the dictionary, the second page. You're looking up the word zoo, right? It's starting in the A's. It's going to take forever to get to the Z's. So what you do is you chop it in half. It's an M. Oh, Z is bigger than an M. Chops another half. Now, what if it is a T? Then we got to keep going. So that turns out to be much, much faster. Binary search is super fast compared to linear search. And sorting is slower than linear search. Sorting is a problem. So we're going to look at sorting. And it's a very important problem, how to rearrange values so that they're in some order. Do we want to do this now, or do you want to quit? We could look at, say, one of these problems here from the lab. After we do that, you're on lab 6 now, or is that where you're at? Which problem do you want to look at?
The third one.
Appending vectors. Okay, let's do this one. So here's a function that takes, called append vector. It takes 2 vectors, a v and a w. Those are vectors of integers. And the 2 vectors, v and w, are passed in. And what the function does, it takes all the values from w and appends it on to v. So v becomes bigger. And that's it. Here's an example. Suppose that v is the sequence 425, the vector 425. And let's suppose that w is 11 and 3. So when you take these 2 vectors and you pass it into the function, you end up getting v to equal 425, 11, 3. It just gets longer. We add the values of w1 to v. And we'll use the pushback function. So let's take a look. And also, by the way, notice it's a void. So we're operating on v. We're modifying v. We're not returning a new vector. And look at this detail here. W is declared as const because we're not going to modify w. We're just going to read from w. But v is not modified with the const keyword because we're going to change v. If we declared that as const, the compiler would not let us include any code that writes into v. And we'll take a look at that. Which lab is this? 6. So this is problem 3. All right, so we're going to implement this function, append vector. And then we're going to call it here. Did I ask for test code? No, I didn't. I should have asked for test code. All the other problems I asked for test code. So you should write test code for this. I may modify the instructions to add test code. So let's create a vector of int v and another vector of int w. And then let's add the data to them. So v dot pushback. And what are we going to pass in there? Let's use the example code 4, 2, and 5. 4, 2, and 5. And W is 11 and 3. 11 and 3. Just going to break it up a little bit like that so maybe I can read that more easily. So there's the test code right out of the problem statement. We call append vector VW, and then let's check the results. V of 0 should still be 4. And V of 1 should be 2. V of 2 should be 5. And V of 3 should now be 11. Before it was undefined. And V of 4 will be 5.
3.
Oh, is it 3? Yeah, 3. Thank you. Sorry. Another little thing we could do in here, we could just have an assert that v dot size is 3. And then after we append, we assert that v dot size is 5. W dot size is 3. 2 rather. Some extra assertions in there, almost like documentation. All right. So that should fail because we just have a stub for the function. Append vector has incomplete type void. What did I get wrong there? Variable has incomplete type void, so it thinks that append vector is it thinks that append vector is being declared as a variable. Why is it doing that? Oh yeah, that's right. Thank you. There we go. We forgot to declare vector. I'll tell you, the compiler didn't help much there. It's hard for C++ compilers to generate good error messages. Other languages do a lot better. That's why it's hard to code in C++ actually, relative to other languages. And keep that in mind. So if you're having trouble in this class with this language, it gets easier when you change to another language. Assertion failed. And we knew that because we didn't implement this yet. So to append, we're going to call pushback on V. You know, for each value that's in W, we need to push back onto V, that value into V. So it'll look something like this. You know, let I range through all the valid indices at W. So we can access all the values. That's how we access all the values of W one after another. And then we just call pushback to get it on there. So we'll need a loop. I'm sorry. So For I is 0, I less than what? So let someone tell me what that should be.
The W dot size.
Yeah. W dot size. So that should give it to us. There we go. You know, it's a lot of work for such a simple function, isn't it? But it's really good for you. It's good practice. There it is. Any others? There's a lot to do. We can look at these on Wednesday, or if there's any, I look at one more now. If we have time for one more, if you want to look at it. 4? 4? Okay. Let's look at 4. Vector insertion. Suppose a vector v contains a sequence of integers ordered from lowest to highest. So it's already ordered, an ordered vector. For example, v might contain these values. We'll use that for test data. Write a function called insert that takes this vector v as the first argument and an integer k as the second argument. The function inserts k into the vector so that it preserves the order of elements. For example, if v were 3, 6, 7, 12, and k were 8, then after calling the function, v would become 3, 6, 7, 8, 12. So we insert 8 into the right position. In your implementation of insert, do not use the insert function of the vector class. So there's already a built-in function to do that. I'm not going to use that. Write code that thoroughly tests the function. The test code should use assertions. So here we have, we'll use some of that. Let's use the example. 3, 6, 7, and 12. 3, 6, 7, and 12. There we go. So there's the, from the statement, from the problem statement. And then we have a function called insert. And the first argument is the vector, and the second argument is the integer to be inserted into the vector. So, vectors have a flexible size. So what we'll do, the trick here is to add on a new value on the end. We'll add k onto the end of the vector, and then we'll swap it with the value in the previous position until we're larger than the thing in front of us. The thing in an earlier position. Let me show you that. So this would be v dot pushback k. There we go, modified v. Now that k is on the end of the vector. So we look at the example code. The vector will look like this: 3, 6, 7, 12, 8. And now 8 is in the wrong position. So what we'll do is we'll go into a loop and we'll compare this 8 to the value that precedes it, in this case 12, and then we'll swap if 8 is larger, if 8 is smaller than the value that precedes it. So while well, V of, so we'll need some kind of current position. Well, V of I is less than V of I minus 1. We'll swap those two values. Well, we already know, we actually don't have to swap it. We know that, we know K, we know the value of K already. So what we want to do is to move the value at V minus 1 into the value, we want to move the value, the preceding value, the value at I minus 1 into position I. And then in position I, replace the K. So after we do this the first time, the vector is going to look like this. 3, 6, 7, 8, 12. And now it's in order, so we didn't have to repeat the loop. So we'll need to create test code that repeats the loop a little bit. Also, I have a bug in here. Well,
You didn't declare I.
I need to, yeah, there's a whole bunch of stuff I didn't do. So integer I, and that'll be v.size minus 1. So v.size, that's one past the, that's a position value, that's one past the end of the vector, so we need to take off 1. See, this is 0, 1, 2, 3, 4. This is position 4. So it's 1, the size is 5, so 5 minus 1 is position 4. And then we need to decrement I. There's another bug in there. Does anyone see it? How about we just, let's use, rather than take that bug out right now, let's use test code to see the bug and then fix it. This vector is not good enough to reveal the bug, but we're going to, we'll start with this. So insert V into V, the value 8. So the result should look like this. V of 0 is 3. V of 1 is 6. V of 2 is 7. V of 3 is 8. And V of 4 is 12. Let's see if that works. No problem. Now I'm going to create another vector, say W, and push back some values. Then call insert. Oh, these should be W. And we'll insert 3. So V of 0 should be 3. V of 1 should be 6. V of 2 should be 7. V of 3 is 8. Does everybody agree with that test case? So we're starting with sorry, it's not V, it's W. where W equals 6, 7, and 12. And after we do the insert, we append it onto the back, but we should shift it forward until it gets into the first slot. This is called a boundary case. You know, the K is not stopping in the middle of the vector. It's going all the way to the front. So you know, I'm testing what's called a boundary case. The other case is if K is bigger than all the values, so it stays on the end. That's another boundary case we can test. Does anybody see the problem with this test? Huh?
The W vector, the last one should be 12, not 8. It's going to fail.
Did I get the test code wrong? Oh yeah, this should be 8, sorry. Yeah. Yeah, the test code is bad. But the code is, there's a bug in the code. I don't know if it's going to break. Let's see. I hope it breaks. That's bad. It shouldn't work. So this test code is inadequate to find the bug. And the bug is the following. That this loop, when I reaches 0, then we look at position V of -1. So we can never let I reach 0. So once K is placed in slot 0, we're done. So we have a dual condition here. We have to have that, that I is greater than 0. It only makes sense to do this when I is greater than 0. If I is 0, then V of I minus 1 is looking in front of the vector. So actually it turns out to be the value that's in front of the vector is, in C++, they don't do what's called range checking. And so the code actually looked at a value that's in front of the vector, and it turns out to be either a 0 or something less than 3. So the code just ran all right for us. It was just an accident that it worked correctly. So this test code, unfortunately, does not reveal, when we ran it, did not reveal the problem. And that is a general problem with the C language and C++. They don't do what's called range checking. In another language, say like Java, that when we tried to index V with an index -1, that would trigger an exception, and the program would terminate unless we caught the exception. So in other languages are much easier to work with. That's one point I want to make here. All right, that's it for